Hey there, it's Jason from Codemanship with a video about modular design principles for JavaScript. Now, in a previous video, we looked at the principles of simple design, that we should make sure that our software works. First of all, any design that doesn't work is the wrong design. And then we make sure that our code is easy to understand, that it clearly communicates its intent. That is, you can understand what the code does just by reading the code. Then we look for duplication in our code, applying the rule of 3, removing duplication to introduce abstractions and generalizations. And then finally, we ask ourselves, is this really the simplest thing we could have done to pass the tests? So if you've not watched that video, I recommend after this one taking a look at that. But simple design we find is really, really good for kind of letting good maintainable working software designs emerge, but often I find that there is more that we need to think about. So we're going to talk about another set of design principles that relates specifically to what we like to call separation of concerns, otherwise known as modularity in our software. So let's just go through the principles of modular design first, and then I'm going to illustrate them with a simple example. First of all, we should make sure that our modules only do one job. There are two good reasons for this. One is that modules that do more than one job, we find they change very often, and also they tend to have lots of clients because they're doing multiple jobs, usually for multiple different reasons, for multiple different clients. So the impact of making a single change can be quite large because we're editing a module essentially that contains other code that might be affected, that has other clients that might also be affected by that. So the risks of breaking larger parts of the software are much higher. But also, when our modules only do one job, if you think about modular hi-fi, for example, if you've got an integrated hi-fi and a modular hi-fi, so in the integrated hi-fi, you get the JVC turntable with the JVC cassette deck, with the JVC CD player, with the JVC radio, with the JVC amplifier, going out to the JVC speakers, and they're all hardwired together. So you only get that one choice as to how your hi-fi system is composed. With a modular hi-fi, you can have the Sony turntable with the Yamaha CD player and the Denon amplifier. You get much more choices about how you can configure your system using existing modules. So the composability of the system is greatly increased when each module only does one job. So make sure your modules only do one job, only have one reason to change. Make sure that your modules encapsulate, they hide their inner workings, particularly their inner data, so the client knows as little as possible about how that work is done. We call that the principle of somebody else's problem. And as we'll see in our example, we're going to have a great example of how making it somebody else's problem introduces a lot more flexibility into the system. Now, the style of design here that we're talking about is called tell, don't ask. So, for example, it's very common in enterprise computing for people to have objects that contain data classes or entities or whatever you want to call them, and then other objects that ask for that data from those data objects and do calculations, do work with them. But then you end up with massive amounts of low-level coupling to the internal details of how the work is done. If you want a decoupled system, what you do is you put the work where the data is, and then the client module just tells the data object, okay, I need you to do that, and doesn't need to know how it's done, doesn't need to know, for example, what data is involved. So the internal workings are hidden from the client, and we call that encapsulation. That's what it really means. You might be thinking, well, but that's an OO concept, Jason, and we do functional programming. Au contraire, mon ami, as you will see, this applies to you functional programmers as well. Modules need to be swappable, usually by dependency injection, so that we can change the implementation of a supplier without having to rewrite the client. The client is not affected by that. How this is achieved will be largely language dependent, but generally speaking, in most languages, we do this by dependency injection, by passing references to objects or functions, as we'll see, into other modules, so they can use them without knowing where they've come from, and very importantly, without binding to their implementation. That's very, very important, so that we can swap that implementation without having to rewrite the client. And then finally, and this is very language dependent, modules should only present what the client needs to see. Now, if you're working in a a statically typed language like Java or C# or C++, if you use a class that has 10 methods on its interface, but you're only using one of those methods, thanks to the wonders of binary compatibility, if I were to change that interface in any way, any of those features, whether you're using them or not, the client will have to be recompiled, retested, and redeployed. Now, this is not the case in dynamic languages like JavaScript. In JavaScript, we bind dynamically at runtime only to the features that we're using. So that's not really a problem. But as we'll see, it doesn't mean that that problem goes away. There's a kind of a mirror image of that, a flip side of that for people working in languages that support duck typing, as we'll see. So there you go. There are 4 organizing principles for designing modular code. And what we're going to do is we're going to look at a little example that I've knocked up here, a very little example. This code calculates quotes for fitted carpets. It needs to know the area of the room that the carpet is going to be fitted in. And then there's a pricing policy. For some carpets, we round up the price, our quote, to the nearest square meter. So if the area of the room is 55.5 square meters, then we would round that up to 56 when we bill for the carpet. But we only do that for certain carpets, not for all carpets. And then we multiply the area, once we've rounded it up if we need to, by the price per square meter, and that generates our quote for the carpet. Now, if you recall the video on simple design, and if you've not watched it, I'll quickly recap here. Let's just see if it ticks all the boxes of simple design. The first principle of simple design is that our design must work. The most important quality of any design. If it doesn't work, it's the wrong design. So I've got some tests, so let's make sure that this is working. Okay, there we go. The tests are passing. So that's box of simple design number 1 ticked. It works. Does the code clearly communicate its intent? Is it easy to understand? I think it is, yeah. I think I can understand what this code does by reading this code. So I'm going to say that we tick that box. Is there any duplication in this code? Not really. So we've ticked that box as well. And finally, is this really the simplest thing I could have done to pass the tests? Probably, if you think about how readable it is as well, and the fact there's no duplication, I think it's pretty simple. I can't really think of a simpler way of doing it. I could maybe think of a clever way of doing it, but not a simpler way. So I'm happy that this ticks all the boxes of simple design. But as I said, that doesn't necessarily mean that we're home and dry. There are some problems with this design. In particular, what if I want to change the way that we calculate the area of the fitted carpet, but not change the way that the carpet is priced? Let's say, for example, it was an L-shaped room, so it didn't just have a length and a width, it had more complex dimensions. Or let's say it's a circular room, they do exist. So we might have different ways of calculating the area. Could I change that independently of the rest of quote? Not really, it's all in one module at the moment. So this module is doing more than one job. It's calculating the area of the room for the carpet, and it's calculating the price for that area of carpet. So what I would want to do to fix this is separate out those responsibilities into their own, first of all, into their own functions. So let's extract a function. Let's call it area. Okay, and as soon as I do that, of course, what do? Sing along if you know the words. Run the tests again. Okay, and similarly down here, calculating this price, this really belongs in its own function. Let's call that function price. And again, immediately rerun the test, make sure it works. Okay, so now area and price are in their own functions. I can just inline that. A bit of cleanup there. Okay. Don't need that local variable anymore. So I'm getting rid of a little bit of duplication there, a bit of redundancy. Okay. Now, these are still in the same module. So whenever I want to change how that's done, I'm having to change it inside the quote module. I don't want that to happen, as you'll see. So what I'm going to do is I'm going to move these. Into their own new modules. Let's call this one area. And we can create that there, nice and easy. So there's 1. And run our tests. Super duper. And rinse and repeat for price. We want that in its own module, so I'll cut that. Paste it into a new module called price. Let's export that. And we go back to quote, that should all be, we can put some semicolons after that if we need to. And retest. There we go. So now we've kind of ticked that first box there. Each of our modules is only doing one distinct job. So if we want to change how the area is calculated, we just need to change it there. Or if we want to change how the price is calculated, we just need to change it there. But, like I said, what if we wanted, for example, to calculate the area of a circular room? At the moment, quote knows a bit too much about how the area is calculated. Those details of the dimensions of the room need to be encapsulated. Now, as I said, you might be thinking, oh, but Jason, this is functional programming. How can we encapsulate using functions? It can't be done. Well, it can be done. It can be done using a mechanism called, do you know? Closures. Let's take a look at how we can do this. First of all, I'm going to surround this area function with a new function that takes a length and a width called room. Okay, and I'm going to return my area function. I'm creating a higher order function here. So you see now that our area function is being returned, and it has no parameters. If we go back to our quote there, you will see that we can now invoke, let's call that room, that's what's actually being, we can now invoke that there directly. So we call room, so room, the outer function there, it's acting a bit like a constructor. So we're passing in the data it needs, but we're going to be hiding that data, as you'll see in a minute, from quote. But we're about halfway through this refactoring, so let's just make sure that it's all working first. Now, here's the clever bit. What we're going to do is we're going to pass that in. So let's add a parameter there. We're going to call that area. Okay, let's make it optional for now. And what we're going to do is we're going to, let's cut that, pass it in from our client, which in this case is the test code, as that final parameter value. Which means I will need here to import the room function from our area module. You might want to rename these modules at some point as well. Okay, so that now is effectively hiding the data that it's involved in calculating an area from quote. Quote does not need to know these things anymore. Let's get rid of these. So again, we go back to our test. So dynamic languages are great, but one of the heavy prices you pay with dynamic languages is without that type information at compile time, it is difficult to automate refactoring. So you'll notice I'm doing a lot of these refactorings manually because it turns out that is the easiest way in JavaScript sometimes. But you'll also notice that I did quite a few of them with using what automated refactorings were available as well. Okay, so we're passing the result of the room function here, which is the area function. That's what it's returning. But the room function knows the length and the width. The area function is able to use those because it's a closure. It's contained within the room function. It has visibility of those. But quote knows nothing about it. It is somebody else's problem. So it could be a round room, an L-shaped room, a square room, a rectangular room, a quadrant, any shape of room you can imagine, really. And quote does not need to know. We've made it somebody else's problem. And we can rinse and repeat this process with, as we'll see, price here. Similar kind of thing. Does it need to know how the price is calculated? Does it need to know about price per square meter and roundup? Or can we encapsulate that? So let's surround price. Let's wrap it up in a closure here. And let's call that carpet. So carpet has this information about whether we want to round it up. And price only needs to know the room area. That's the only information we will give it. And then carpet is going to return the price function. So again, if we go back to our quote here, now we can call that carpet function here directly. Looking good. And a similar kind of thing. We can introduce a parameter for that function. So it's passing our price function in from the outside. And then that's the value that we will pass in from the tests. So there and there. And again, we'll need to import that. From our price module. So now, hopefully, when I rerun my tests, let's just check that that works. It's all still working now. That means I can get rid of these. And now our quote function is starting to look very simple. It's just a composed function. That is, it's a function of it's a function that just calls other functions. It's a higher order function because we're passing functions in as parameters. Let's go back again and oops. Okay, lovely. Now look at quote there. So it doesn't know that calculating a room area involves length and width. It doesn't know that calculating a price is determined by whether or not we need to round up or the price per square meter. It doesn't need to know any of that. And that's what we mean by separation of concerns. We've made that somebody else's problem, and it's a very powerful thing. Because quote doesn't need to know these things, it's now possible to change how the area is calculated and how the price is calculated independently of quote. Quote does not need to know. It doesn't need to change. So those are the first two principles of modular design. Principle number one, each module should only do one job. Each module should hide its inner workings, should encapsulate in particular its inner data, so that clients know as little as possible about how the work is done. They just tell that module to do the work for it. And because they know as little as possible about how the work is done, it becomes much easier to change how the work is done without having to rewrite lots and lots of client code. Very important. Now, the third principle of modular design is that modules should be swappable by dependency injection. And if you think about it, if you've already noticed, that has already happened. As a side effect of introducing these closures, that has already happened. I've already done that. These functions are being passed in. So let's demonstrate the power of that let's say, for example, in this test, that I don't care how the area of the room is calculated. So I can stub that. I can just introduce an arrow function here that returns a hard-coded test value, a test area of 150. So I'm passing in a completely different implementation, and you will note that I didn't have to rewrite a single character of the quote module there. It stayed exactly the same, because it just depends on the signature of that function. That's all it needs. As long as that function has the right signature and, of course, conforms to the contract of calculating an area. So if it, for example, it was to return true or false, we would have a bit of a problem here. Well, in JavaScript, maybe not, but in other languages, we might have a bit of a problem here. So as long as it fulfills the contract, it looks the same and works the same from the outside, that's what we really mean by duck typing. If it looks like a duck and it walks like a duck and it quacks like a duck, then it's a duck. And there you go, there's our duck. It doesn't matter, quote doesn't need to know. And this becomes very, very powerful. We can dynamically change how the area of carpets are calculated without rewriting quote. And you can imagine probably many situations where you would want to swap one implementation for another without having to rewrite your core logic. For example, swap an Oracle database with a SQL Server database without having to rewrite your business logic. So it's very important that your business logic is cleanly separated from that external dependency. And that's how we achieve it. So another thing I'm just going to quickly mention here, and it's a good job we're looking at a test. So I'm passing in a stub implementation of a function that just returns a hard-coded value there for the purpose of our test. Now, modularity and unit testability kind of go hand in hand. If our code is not modular, then it's not going to be unit testable. For example, if we have code that embeds external dependencies in a way that can't easily be replaced by dependency injection, then we can't stub it or mock it. And it means, therefore, we end up writing what are essentially integration tests that are going to run a lot slower. So modularity and unit testability very much go hand in hand. And it's a kind of a chicken and egg situation in the sense that you want your code to be modular so that it is unit testable. But if you do test-driven development and you're in the habit of using stubs and mocks, for example, for external dependencies, then you're going to end up with designs that are necessarily more modular. So TDD tends to produce code that is more modular and, as a self-fulfilling prophecy, is more unit testable. And more modular code is easier to unit test, and therefore these things kind of go hand in hand. Okay, now there's one final principle that I mentioned, which is about interfaces. So this is not something that you really need to worry about in JavaScript because we have duck typing and you're only binding at runtime to the features that you're using. So it doesn't matter what other features a class has, for example. If you don't reference them, you don't call them or use them, then it's not going to affect you. But that's not to say that we don't need to think about what each module depends on that it's not using. If we take a look at our quote module there, take a look at the imports there. These imports are now unused, but if, for example, I were to move the area module to there, in fact, if I do that, it'll probably update it. Let's pretend we didn't do that. So it hasn't updated any of the references there. Now if I try to run my tests, quote is broken, basically, because I've changed something that I should not have changed. Let's just move it back. So I'm depending there on an implementation that I don't need to depend on. So let's get in the habit of cleaning up our imports and that kind of thing, looking for references we're not using. So that's kind of the flip side. The mirror image of client-specific interfaces is that as clients, we shouldn't depend on things we're not using. So clean up those imports. And talking of imports, take a look at the imports in quote. There are none. And in price, there are none. And in area, there are none. If we take now a look at the test, so this is at the top of the call stack, that's where all of the implementation dependencies are. It's only the tests, the ultimate client, the top level client, that actually knows what implementations of the quote function and the area function, the price function it's actually using, where they're coming from. And this is a sign of good modular design, was we compose our systems from the outside using dependency injection. So all of our dependencies are injected. A bit like Russian dolls, the way that we construct a call stack is a bit like Russian dolls. So we pass a function into a function into a function, or we chain functions using currying or something like that. Or if we're doing object-oriented design, we pass objects into objects into objects. So that each object, when it calls the features of other objects, or each function when it calls another function, is not binding to its implementation. That is determined on the outside. And we call this inversion of control, that the actual sequence of function calls or method calls is not determined by each method or function. It's determined using composition from the outside. And you can probably imagine, you probably know of and have used many, many frameworks and design patterns that like Model View Controller, for example, that depend on that inversion of control, that the flow of the user interface, the MVC flow, if you like, is not determined by each view or each controller. It's determined from the outside by composition in some kind of way using dependency injection. Okay, so there you go. There are 4 principles of modular design, very closely related to unit testability. And as you're going to see in a later video, very closely related to how we deal with legacy code. It's a very, very important subject. Very, very hotly debated very often, and people often get blinkered about, well, I'm doing functional programming, so this stuff doesn't matter to me, because a lot of people call these object-oriented design principles. But hopefully what you've seen here is that it's not necessarily about classes and objects. It's about modules and features and functions as well. Okay, there you go. Modular programming in JavaScript.